All right, for problem number 1, what we want to know is how many grams, or what is the mass of sodium in a sample of 8.5 grams of the following substance. The first one, NaC7H5O2. So basically what we want to do is figure out, if we have a sample of 8.5 grams of that substance, how many grams of sodium is in that sample. So as always, the very first thing we want to do is we want to write down what we are given. And what we are given is that we have 8.5 grams. And grams of what? We have to write down the whole thing. So it's NaC7H5O2. If you don't write this down, then you're going to get confused at some point. I can virtually guarantee it. So don't just write down grams. Write down grams of whatever it is you're talking about. Now, before we even do anything else, in almost all problems, it's a good idea when you have a compound or a molecule or whatever that you're dealing with to find the molar mass of it first, because you're almost always going to use it. In a chemical reaction, we're definitely going to use it. In these conversion problems, we're almost always going to use it as well. So even without thinking about what we want to do next, let's go ahead and figure out what the molar mass of this compound is. So it's Na, and then it's C7, then it's H5, and then it's O2. So we just have to go down the path here. So how many sodiums do we have? We have 1, and when you look on the periodic table, that's 22.990, okay? And then we have 7 carbons, so we have 7. Carbon is 12.011 grams per mole, so that comes next. We have 5 hydrogens, so hydrogen 1.008 grams per mole. And finally, we have 2 oxygen, so 2, and then we have 15.999. Now notice I didn't refer to my periodic table over here, because the skill of taking a random compound or molecule and calculating the molar mass is something that you should know how to do. I'm still going to write it out so that you get a little practice. Eventually, maybe I'll even stop doing that, but let's take the training wheels off. You know how to find these masses. These come directly from the periodic table. All right, now whenever we do the multiplications in addition, 7 times this number, and 5 times this number, and 2 times this number, and then add all the numbers up together, we get 144.105 grams per mole. Of what? What are we talking about? Well, it's NaC7H5O2. All right, now what are we trying to find? We are given that we have a 8.5 gram sample of this, and we want to figure out how many grams of sodium are in that sample. So you ask yourself, what can I convert to get me closer? Well, I know grams of this, and because I know the molar mass, and I can find the molar mass of anything, I can find out how many moles of this substance that is. So I'm going to use this conversion factor, 144.105 grams. Grams of what? Grams of NaC7H5O2 for every 1 mole of what? NaC7H5O2. And I know you're rolling your eyes. You're saying, why do I have to write this down every time? You're just going to have to trust me that you will make less errors if you do that. Now, the grams cancels with the grams. So if you do this division here, just the way it sits, you're going to know and calculate the number of moles of this molecule. But that's not what we want. We want to figure out the number of grams of sodium. So how do I inch my way there? I need to somehow, instead of talking about the whole molecule, I need to be talking about just the sodium part. That's the only way I can get to grams of sodium. So the way I bridge that gap is I say that in every 1 mole of this substance, as a whole unit, there has to be 1 mole of sodium, because there's 1 sodium atom for every one of these groupings. So the way you write that is you say 1 mole of the whole thing. Write the whole thing down. NaC7H5O2. There has to be 1 mole of sodium atoms, essentially. And the way you can write that is 1 mole of sodium. You know that means atoms. So this is going to cancel with this. Now, if you stop the calculation here, you take this times 1, divide by this, times 1, divide by 1, you now know the number of moles of sodium in that sample, the number of moles of sodium. But we want the grams of sodium. We can always convert from moles to grams. So we continue on the next line here. And we need the molar mass of sodium. Now we can go back to the periodic table. It's the first number here, the 22.990 grams per mole. So what you want to know is, or what you want to write down is 22.990 grams of sodium, right, in every 1 mole of sodium. Now you arrange it this way, whoops, Na, because the moles of sodium will cancel with the moles of sodium, and you have grams of sodium on the top. So the question says, how many grams of sodium are in a sample of 8.5 grams of this substance, right? And so we start with the grams of that substance, convert to moles of the substance, and every 1 mole of this substance, there's also 1 mole of sodium, so we get to moles of sodium, and then from moles of sodium to grams of sodium. So 8.5 times 1 divided by 144.105 times 1 divided by 1 times 22.990 divided by 1, and what you get is 1.36 grams of sodium. And that's the answer. Now you see what I was trying to get kind of in the beginning here. Don't try to map out a path from the starting point to the finishing point in your head, because it's just going to get difficult. It's going to get, I shouldn't say impossible, nothing's impossible, but it's going to get much, much harder to do that. It's better to write down what you know and slowly convert and do the calculations that you know are legal, inching yourself toward the answer. All right, so last problem of this type, we have an 8.5 gram sample of Na2C6H6O7. We want to figure out how many grams of sodium are in an 8.5 gram sample of that substance. So we do the same thing again. We write down what we know. 8.5 grams of that substance, which is Na2C6H7, whoops, H6. H6O7. And actually, even before we do that, what I think I'm going to do is I'm going to erase this. Let's find the molar mass of this, because we know we're going to need it, and so let's just go ahead and do it first. So we have 2 atoms of sodium here. So 2 times the 22.990, that comes right from the periodic table. We have 6 atoms of carbon, and that's 12.011 grams per mole. We have 6 atoms of hydrogen. We'll continue on the next line, 1.008 grams per mole. And then we have, this is O7 right here. That's going to be 7 times 15.999. All right, so for the substance Na2C6H6O7, we have a molar mass, the 2 times this number, and then the 6 times this number. The looks like I made a small mistake here. There's a 6 right here, because 6 hydrogens times this number, and then 7 of the oxygen molar masses. You're going to get a number when you add them together of 236.087 grams per mole of this substance. Okay, so now we write down what we are given. We are told that we have an 8.5 gram sample of this substance, Na2C6H6O7. So that's grams of that substance. So go ahead and continue that across. Anytime we start with grams, we can automatically convert to moles. Why and how? Because we just figured out the conversion factor right here. So in 236.087 grams of this substance, of Na2C6H6O7, there is exactly 1 mole. Mole of what? Na2C6H6O7. All right, so we write it on top and bottom like this, so this will cancel with this one. If we stop the calculation now, we would be calculating moles of this substance. All right, now we have moles of the substance, but we want to talk about sodium, so we have to bridge that gap. And let me just go to the next line, probably, just to make it not crowd. And what we can do is we can say that in 1 mole of that substance, Na2C6H6O7, in 1 mole of this, how many moles of sodium do we have? Well, there's 2 atoms of sodium for every one of these units, so there has to be 2 moles of sodium. 2, whoops, no, let's not capitalize it, let's not get confusing, moles of sodium. And sodium meaning atoms there. Now on the bottom, I have the moles of this substance. On the top, I have the moles of that substance, so those cancel. If I stop the calculation here, I now have the moles of sodium. But I don't want the moles of sodium, I want the amount of grams of sodium. And I know the molar mass of sodium, and so I write that down as 1 mole of sodium atoms. And I got to go back and get the molar mass, but I've used it so many times, it's 22.990. 22.990 grams of sodium. Now on the bottom, I have moles of sodium. On the top, I have moles of sodium. So we start with grams of the substance, convert we're using molar mass to moles of the substance. And then in 1 mole of that substance, there must be 2 moles of sodium because of the formula. And then in 1 mole of sodium, we know the grams, the amount of mass here. So if we take 8.5 times 1, divide by this, times 2, divide by this, times the 22.99, and then divide by 1, we get 1.66 grams of sodium. 1.66 grams of sodium. So really the only difference between these two problems, other than that the formula is different, is notice in this one there was only 1 sodium atom for every one of these units. So there was a 1-to-1 correspondence here. But in this formula, there was 2 sodium atoms for every unit. So there was a 2-to-1 correspondence here. If you try to keep track of all this stuff in your head, you're going to make a mistake. So you just start with what you have, and you slowly progress and see what makes sense to calculate to get closer and closer to calculating sodium, which is what we were trying to do. Okay, let's take a look at the next problem. Deceptively simple problem. Simple once you know how to do it, of course. But sometimes you stare at these and you don't know what to do. Let's read it. What is the mass of 500 atoms of iron? 500 atoms of iron, Fe. All right, so this is a very weird problem. It's some number of atoms of a substance, but it's also just 500 atoms. That's almost nothing. That's almost no quantity of iron. What do? Same thing you always do. Write down what you are given. Do not try to map out a path to the solution. So I write down exactly 500 Fe atoms. Or you could write it as atoms of Fe. I mean, it doesn't matter. But you want to write down that it's atoms, and you want to write down that it's iron. Iron is Fe. You want to figure out what the mass of this is. So you want grams, but you're starting with atoms. So how do I figure out, how do I start to convert and get a little closer from atoms to grams? Now, there's no direct bridge that goes between the two. However, you can go from atoms to moles. Why? Because a mole is 6.02 times 10 to the 23rd atoms. In this case, we're talking about iron, so it's atoms. So you can say that 6.02 times 6.022 times 10 to the 23rd Fe atoms is the same thing as 1 mole of Fe atoms. Right? And on the top you have iron atoms, on the bottom you have iron atoms. Okay. And so if you conclude the calculation here, you have moles of iron atoms, moles of iron, right? How do you go and get the convert to grams? Well, we know moles, and we know that iron is on the periodic table 55.85. That's grams per mole. So I can use that as a conversion factor, and I can say that it's 1 mole of iron atoms is the same thing as 55.845 grams of Fe atoms. All right, so the moles of iron and the atoms and the moles of iron atoms cancel. So now what do I have left over? Grams of iron. The word atoms you don't really need there, but grams of iron is what you have there. So if you take the number 500 times 1, divide by Avogadro's number, times 55.845, divide by 1, you will get 4.637 times 10 to the minus 20 grams of iron. Now, if you drop the word atom, since you know iron is an atom, but we'll just put it here for completeness. All right, so 4.637 times 10 to the minus 20. So it's a very, very small mass of iron atoms, of course, because you only started out with 500. Not 500,000, not 500 trillion, just 500. That's nothing. That's almost nothing. So the answer is a very small number of grams. All right, now we have 4, let me see, how many do we have? Maybe not 4. 2 problems that are similar, but not quite the same. So in the next 2 problems, we're asking ourselves, how many nitrogen atoms are there in a 5-gram sample of each of the following? And the first one is called glycine, C2H5O2N. So we're starting out with a 5-gram sample of that, and we're talking about glycine. So you pretty much know you're going to need the molar mass of glycine. You're almost always going to need the molar mass of whatever it is you're talking about. So you know that it's glycine, and that's C2H5O2N. So my advice is just calculate the molar mass to begin with. There's 2 carbon atoms, so it's 12.011 grams per mole. Then you have 5 hydrogens, 1.008 grams per mole. And then you have 2 oxygens. So let's go down here. You have 2 oxygens, 15.999. And then finally you add the nitrogen, which is 14.007. Let me double check all my numbers here. I have them mostly memorized, but that's just because we use them so much. Anyone can make mistakes, including me. So C2H5O2N, multiply, 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 add them all together, you'll get 75.067 grams per mole. All right, so that's a good starting point. Now, what are we told? We're told that we have a 5-gram sample. So I'll put 5-gram sample of what? C2H5O2N. And what we want to calculate is how many nitrogen atoms. So we're not asking how many grams of nitrogen. We're not asking how many moles of nitrogen. We're asking how many nitrogen atoms. So the unit that we get at the end should say nitrogen atoms. So we have to be very, very careful in how we convert this. So we don't have the whole thing mapped out, but we're starting from grams, and we know we can go from grams to moles of anything, so we're going to do that first, right? So we know that in 75.067 grams of the substance, C2H5O2N, is exactly 1 mole of this substance, C2H5O2N. And we arrange it upside down like this because we want the grams of the glycine to cancel with the grams of the glycine. All right. Now, if we stop the calculation, we have calculated the moles of glycine. But we don't want that. We want to figure out how many atoms of nitrogen we have, right? So we don't want to be talking about the whole thing. We want to be talking about the nitrogen. So we have to use the formula that we have here to go a little deeper. We know that in 1 mole of this, there's 1 mole of nitrogen because there's 1 nitrogen atom for every 1 grouping of these things. So in 1 mole of this compound, C2H5O2N, there's exactly 1 mole of N. 1 mole of N what? Let's call it what it is, atoms. So 1 mole of nitrogen atoms. Okay? But that's not what we want, because we don't want moles of nitrogen atoms. We want atoms. We want how many atoms, right? So let's go ahead and cancel this. Moles of this and moles of this. We have to do one more conversion on the next line, and it's, of course, attached to the end of this guy, okay? We have mole of nitrogen atoms. 1 mole of nitrogen atoms is what? It's equal to 6.022 times 10 to the 23rd, what? Nitrogen, what? Atoms. Because we're talking about just the element nitrogen that's inside of there, and so it's an atom. And so the moles of the nitrogen cancel with the moles of the nitrogen. Let me catch up with myself and just make sure I've done everything correctly. So let's go ahead and multiply this out. If you take the 5 and you multiply by the 1 and divide by 75.067, multiply by 1, divide by 1, and then multiply by 6.02 times 10 to the 23rd, you will get 4.011 times 10 to the 22 nitrogen atoms. Is that what the problem asked us? The problem said how many nitrogen atoms are there in a 5.0 gram sample of glycine. So we start with 5.0 gram sample of this. We convert grams of that stuff to moles of that stuff. So now we're at moles. Then in every 1 mole of these, there's also 1 mole of nitrogen atoms. So now we're at moles of nitrogen. And in every 1 mole of nitrogen, we have this many nitrogen atoms. So now we have arrived at the unit that we want. And it's a very big number because there's a lot of atoms there. Okay. Now we want to do the same exact problem, essentially, but we'll change the compound. And this is the last problem. So the difference here is we have a 5.0 gram sample of, in this case, in the next problem, magnesium nitride. Magnesium nitride, 5 gram sample. We want to know how many atoms of nitrogen are in there. So what we know is it's a 5 gram sample of magnesium nitride. All right. Now, before we do anything else, we need to notice we were not given the chemical formula for that. So we need to figure out what magnesium nitride actually looks like. So we know magnesium is going to be Mg, and we know nitride is going to be the element nitrogen, right? So what is the charge? This is going to be a metal plus a non-metal. What is the charge on this magnesium going to be? It's going to lose 2 electrons. So the charge in the magnesium will be a positive 2. The nitrogen would like to gain 1, 2, 3 to look like neon. So it'll have a charge of negative 3. And so when you do the crisscross here, you'll get Mg3N2. So we didn't give that to you in the problem statement, but it's magnesium nitride, Mg3N2. So what you do over here then is you say, well, I'm almost certainly going to need to know the molar mass of this. So I'm going to say Mg3N2. Let's figure out what the molar mass is. There's 3 magnesium atoms, 24.31, and the nitrogen we already know is just a little bit over 14. So we're going to use the number 24.305 for magnesium grams per mole, and then there's 2 nitrogen, so it's 14.007 grams per mole. So for Mg3N2, when you multiply, and then add them together, you get 100.929 grams per mole. All right, so that's something we know we're going to need later. Now for the problem statement, we're starting out with a sample, a 5-gram sample of this compound. So we write down 5 grams of what? Mg3N2, magnesium nitride, okay? Now we draw our bar here. Now we know we start with grams, we can definitely convert to moles, so we do that. We know that that's going to get us closer to what we're trying to reach. So in 100.929 grams of this substance, Mg3N2, that's exactly equal to 1 mole of Mg3N2. Now, of course, the grams of magnesium nitride cancel with the grams of magnesium nitride. All right, now next part of the step is now if we stop the calculation, we're left with moles of magnesium nitride. We want to figure out how many nitrogen atoms there are. So we have to zoom into what the nitrogen is. So we need to go from learning about the whole unit here to just the nitrogen. So we know in 1 mole of this, of Mg3N2, there must be 2 moles of nitrogen what? Atoms. Because that's what we're talking about here, right? So this is a mole of Mg3N2, moles of Mg3N2, right? So if we had stopped at moles, that would be how many moles of this substance. But now by basically multiplying by 2, that's the number of moles of nitrogen atoms we have, right? But we don't want to know the number of moles. We want to know the actual number of atoms. And so what we say is that in 1 mole of nitrogen atoms, that's the same thing as 6.02 times 10 to the 23rd nitrogen atoms. Right? So the moles of nitrogen cancel with the moles of nitrogen, and the unit left over is just the actual number of nitrogen atoms. So if you take 5, multiply by 1, divide by 100.929, then multiply by 2, divide by 1, then multiply by 6.022 times 10 to the 23rd, divide by 1, you will get a number which is 5.967 times 10 to the 22 nitrogen atoms. So again, don't try to map this stuff out in your head because something will trip you up eventually. The ratio of nitrogen to the whole unit might trip you up. Any one of these things might trip you up trying to do it in your head. So instead, you write down what you know. You know the number of grams of this substance. And then you don't know what to do, but you know you can legally convert to moles. You have the molar mass, you convert to moles of this substance. But you want to know more about the nitrogen that's going on. Not the moles of the whole thing, but just the nitrogen. The path through that is to know that 1 mole of this unit must contain 2 moles of nitrogen because there's 2 atoms for every one of these whole units. So 1 to 2. Notice how the unit is very explicit, moles of nitrogen atoms. And then for every 1 mole of those atoms is the gigantic number of nitrogen atoms there. And then when you do it, you get, of course, a very large number of nitrogen atoms. All right, that'll do it for this lesson. We have 2 more lessons after this just to get a little more practice. It's very important for you to get comfortable with moles, with atoms, with molecules, with formula units, with grams, and just to be able to fluidly think in your mind how to do it. But do not try to make a path from the start to the finish. You write down what you know, and you ask yourself, what can I do legally? You don't want to invent anything new. I don't want you to invent anything. I want you to apply what I've taught you and do what's legal. If you have grams, go to moles. If you have moles, go to grams. Figure out how to inch yourself toward the answer to where you're trying to go, and then through practice, you will get there. It does take practice. So practice all of these. Follow me on to part 3 of calculating with moles. Learn anything at mathandscience.com.